Okay, welcome everyone. This is the week 10 webinar. All right, we're getting really close to the end. In fact, after this webinar, there's only one more because we have our week 11 and then it's finals and that's it. So this is the week 10 webinar. And I want to talk about what we're doing today. Today actually might even be the most important day in terms of what people use. It's a really, really important piece of statistics. It's something that you've probably all heard of, but didn't know a lot of the details. And today we'll do some of the details. We can't do all details because this is an elementary stats class, but we'll do some of it at least. So as always, I'll start out with Q&A. And then we'll talk about what a scatter plot is. So scatter plots are really important. They come up and we'll get into what is a scatter plot. So it's a way of graphing a bunch of points. Then, I know this looks really easy, the letter R. Turns out R is really deep. And R is a letter that is not the first letter of what it stands for. Isn't that weird? So R represents correlation. And you've all probably heard the word correlation. You might even have used it without really knowing what it meant. But we'll have a better idea of what it means by the end of today. You won't fully know because there's a lot of math behind it, which I can't do, but at least we'll talk about, how to think about R. And then we're going to do something that looks really easy. If you know R, we'll talk about R squared, which is, by the way, the square of R. Sounds easy, doesn't it? But it turns out there's a really different interpretation of R squared than there is of R. And we'll talk about that and how you interpret it and how useful it is. Then we'll look at the equation of the regression line. You might have heard of the regression line. And we're going to get into that. And hopefully you remember how to find an equation of a line, or at least know what an equation of a line means, because that's a big piece of today. There's a little bit of basic algebra in this chapter. So we'll talk about that, and it's basically lines. And then, as I see you wrote, correlation does not mean causation. So avoid causation. That is a major trap, not just students fall into, but I see it all over the place, where they find a correlation and then they start talking about cause. And you cannot say the cause is happening after finding correlation. So it's very, very, very important. So many people make that mistake. So do not make that mistake. Now I'll talk about some of the ways of avoiding the mistake and some of the verbiage that you need when we're going into what's called regression analysis, which is what this chapter is, chapter 12. And then, as I promised a few weeks ago, every week has hypothesis testing. So we're going to have a hypothesis test. And anyone know what this letter is right here? It's not P, by the way. Anyone know how to pronounce this letter? Yeah, it's the Greek letter rho, like row, row your boat. Yeah, it's not phi. It's the Greek letter rho. And it's like the Greek letter for R, and that's why it may look like a P, but that's not what the Greeks think. And that's going to be the population correlation. So we're going to have a hypothesis test to see if there's a correlation for the entire population or not, given a sample. And that is the plan. And I want to mention this is, again, week 10. What's important about the number 10? Yeah, 10 is an even number, which means there is an exam this week. So be ready. Be ready to take the exam. Yeah, we're also close to the end. There's 12 weeks in this class. So this is week 10 of 12. And the last week is actually one of the lightest weeks, because the final is the same as a regular exam. So it's actually an easier week, it turns out. But, this week is a regular even week. So we have to do that. I also want to remind you about the project. So, because you asked, the project is due a week from Sunday. So it's 13 days from tonight. But do not wait until a week from Sunday to start the project, please. Right? You should already know what your project's about at this point. If not, please post it on the project discussion forum and I can let you know if it'll work. And hopefully, maybe you've already collected data at this point too. So it's time to start working on the project. The hope is maybe a week from tomorrow or so, you can send me an email with your project draft. So will the final prioritized content from only week 11? So week 11 will be more heavily weighted than the other weeks, but all the other weeks are, so the other weeks do matter also. Yeah. Okay. And you submitted yours to your team. So hopefully you understand that I don't take breaks during our webinar, so I won't see it. And I actually have a meeting. I have a meeting that starts during our webinar. I'm gonna be late to it. So I probably won't get back to you until tomorrow because my meeting lasts until like 9 o'clock or so, maybe 8:30. So sorry about that, but tomorrow morning. So today is that one of those, I don't know if you've had one of those super busy days, but I have had no break today. I will have no break from 10 a.m. till 8:30 p.m. tonight. So just let you know, or no more than a bathroom break. So I haven't had a chance to look at much of anything. Sorry about that. But that happens. We all have lives, right? Tomorrow I have an easier day, so I'll definitely have lots of time tomorrow. And then this morning, early morning, I graded your discussion posts. I don't know if you noticed, but I woke up. I don't know if you ever wake up at 3 in the morning, but that's what I did. Not on purpose. Yeah, so chapter 11 is going to be a little bit more content than the rest of the chapter for your final exam or the week 12 exam. And the week 12 exam is worth just as much as the week 10 exam, which was worth just as much as the week 8, etc. Okay. Yeah, and again, if you have questions on the project, post on the project discussion board. That's better than an email. Because especially if other people can benefit from it. The only thing you can email me about is there's something personal that you don't want to tell anyone else. Then you could email so there's not public. Okay, other questions? Good questions, though. Really good questions. Because we are getting towards the end. Hopefully you're finding this a useful class. I'm not even going to pretend it's easy, but it's definitely, definitely useful. I think it's the most useful math class there is. All right, you ready for going into chapter 12? And I want to remind you, there's only 13 chapters in this whole book. We're almost done. And chapter 13 is one of the easiest chapters in the book, by the way. So I can kind of end light, but 12 is hard. Okay, 12 takes a lot of work. All right, so I got a survey question for you. And you have to answer it. If you don't feel comfortable, you can lie. I'm not going to say your name when I post the numbers. But there's 2 questions. First, including yourself, how many siblings do you have in your family? That's question 1. And how many minutes do you spend exercising in a typical 7 days? And I'll probably answer it also. You could call half siblings. You can so a half sibling would be a half. So if it's you and another sibling and another half sibling, that would be 2.5. So maybe I'll answer. I'm typically an outlier, not in siblings, but I exercise more than anyone I know, basically. So you have to write down how many, so you're going to write down how many siblings, including yourself, and how many minutes a week do you exercise, typically. And I want all of you to answer. Okay. And by the way, was my promise right that I'm probably an outlier when it comes to exercise? I'm a major exerciser. And that's what I like to do all the time. Sometimes I even exercise while I grade. I'll like march around while grading. Okay, so here we go. We have a bunch of data values. What we want to do is we want to look at this, we want to see, is there any kind of relationship between the amount of siblings a person has and the amount of exercise they get? Okay, does that make sense? So what I'm going to do is I am going to go to the calculator. And any guess on what calculator I'm going to use? Yeah, 24, because we only have this week and next week. This is this chapter and the next one. That's it. Regression analysis. And chapter 12 is the chapter on regression analysis. So that's where we are right now. And that is our second to last chapter. We're almost done with this course. So I'm going to click regression analysis. Check something. Hopefully you can all see it. And I think the easiest way, I could do it by point, but I think the easiest way is to put all the X's in order, and they have to be ordered. So our X's were 4, 5, 1.5. And then we had 3 and 6. And the Y's, I think the easiest way, the Y's, because the Y's are bigger. I'm going to copy the whole thing and just get rid of what I need to. The Y's were 1,220. As I said, I'm intense. Then we had 100. Then we had 260. Then we had 140. Then we had 315. Any questions on the X's and the Y's? Because these are points, and you usually call the first variable or the first coordinate X and the second coordinate Y. Is that clear so far? Then I'm going to click on plot points. And we can see the points plotted. And what do you notice? What we want to do is we want to look at the points and see if there's a line that's a pretty good match to the points. Does it look like it? Doesn't look great, does it? Yeah, it doesn't look like there's much of a match. The points are kind of all over the place. You know, there's always a line, by the way. And I'm messing that with my fitness. Yeah, and like I said, I am intense. Okay, it's what I like doing. Okay, so we have our points, and we see that this line is not really a good estimator of where the points are. The points are not that close to the line. Do you see that? So there's all kinds of things, and I created this calculator so that we can, find this stuff. And it does lots of things, and I go over all these things one at a time. So the first thing I want to talk about is R. That was, if you remember, that was the first item of the list of things to talk about. Okay. You're not supposed to scatter plot your project, by the way, because your project shouldn't have anything from regression analysis. Scatter plot, I mean, your project should all be about confidence intervals for a difference and hypothesis tests for a difference. Don't touch regression analysis. Got it? Because there's reasons. I used to have a project 3 on regression analysis, but it was just too much work for the students, so I stopped it. Maybe you all wanted a third project, but usually not. Okay, so we have R. So R is always a number between -1 and 1. If R is close to -1, that means that line is going to be really close to the points, but the slope of the line will be negative. If R is close to +1, that means the line will be close to the points and the slope will be positive. If R is close to 0, that means the line is not close to the points. You see, like this point right up here is way away from the line. The others aren't that close either. Do you see how that works? So R tells you the correlation. Any questions on that? Okay. And it tells you whether or not having a linear regression model is a good idea. And if there is almost no correlation, the regression model is kind of a waste of time. So in this case, the regression model is a waste of time. Now, I didn't know that because I didn't know what you guys were going to say when I asked you the survey question. Again, you don't know it until you're done. Sometimes you can guess, but you don't know it until you actually look at the data. Any questions on that? So that's what R corresponds to. So let me go back. So again, R is a correlation. Make this a little bigger so you can see and actually. So R is called the correlation. R is between -1 and 1. It can never be bigger than 1. It can never be less than -1. The sign of R is the same as the sign of the slope. If R is close to -1, the points are close to all being on a negatively sloped line. If R is close to 1, the points are all close to being on a positively sloped line. If R is close to 0, then there's no line that fits the points well. Okay, so if I drew some other line, like that one, from up to down or something, the points still aren't going to be close. There's no way to get all the points real close to the line. Okay, typically you can't get the points right on the line, but sometimes you can get them somewhat close. Okay, here we weren't able to do that. Okay, so I like to look at the best example. I mean, we have an example where R is close to 0, but one that you can all picture and you've all seen it, especially if you live in Tahoe. If you live in San Francisco, you may not have seen it very much. And that is the night sky, when you can see all the stars. So if you live in San Francisco and LA, you may never have seen stars. But in Tahoe, we have beautiful stars when there's no clouds. And there isn't any kind of line that those points are close to. Does that make sense? Okay, so that is kind of an example. The night sky is, I think, the best example. We're going to have an R that's really close to 0. Let me give you some more real life examples. I'm going to have you see if you can think of some. Okay, so if R is equal to 1, if it's exactly 1, let's make this a little bigger. Let me give you an example. Let's suppose that X was how tall you are in inches, and Y was how tall you are in centimeters. Do you know why that's exactly 1 for R? Anyone know? When I say it, it'll make sense to you. You probably all have heard it before. You may not remember it. Has to do with inches and centimeters. Anyone guess why? They're proportionately correct. Might be the right idea. Yeah, because there's actually a formula where if you know how many inches you are, you know how many centimeters you are, and it's a linear formula. Does that make sense? There's a perfect formula. Same thing if it was, say, temperature in Celsius and temperature in Fahrenheit. There's a perfect formula. Does that make sense? So R would be exactly 1 in that case. Okay. Can you come up, let's see in the chat box, if you can come up with an example, a real life example, where R equals 1. That's not the example I gave, but a different one. There's lots of them. Okay, good. I like that. How many dollars, at this moment, how many dollars versus how many yen? Because there's a perfect linear fit and it's a positive slope. If it's worth more dollars, it's worth more yen, and there's a formula for it. I personally don't know exactly how many yen to a dollar. It's around 100-ish because it changes every day, but there is a formula for it if you went online and looked to some website. Any other ideas? Time in the Pacific zone versus time in the Eastern time zone. So that turns out that would be right if you said, but we're only going to be looking at maybe an hour or 2 time distance. Because remember that after 12:59, you get to 1. So all of a sudden things break. Weird things happen. But yeah, you get the idea. That definitely would be one, other than the weird time flip thing. And then there's the other issue that some places, and this is the important thing, what was the big thing about time yesterday? I think you all know. Yeah, daylight savings, but not all countries have daylight savings. So that wouldn't work if you looked at it throughout a whole year where one country had daylight savings and one didn't. But you'd still have actually a very high correlation, but it wouldn't be exactly 1. Do you see? But if you were looking, say between 6 o'clock p.m. and 9 o'clock p.m. here versus 6 o'clock p.m. and 9 o'clock p.m. in Arizona, that would be a R equals 1. Does that make sense? Okay, so now let's come out with the next one. Let's see if we can come out with a real life example. And I'll do mine and I'm gonna let you do one yours after. And I've already done a few, but we'll do more. Think of a real life example of 2 survey questions where R is very close to 0. And here's an example I have that I got ready for. And again, this whole thing about siblings and exercise, that for our 5 people R was close to 0, but that may not be true for the whole population. But how about the temperature in South Lake Tahoe? And what's the total number of points in the soccer game in New Zealand for the high school in the city there? Why do you think R would be 0 or really close to 0? Yeah. If you knew what the temperature was in South Lake Tahoe, do you have any idea what how high scoring the soccer game is going to be in some high school in New Zealand? Does that make sense? Yeah, it's not because one has low scores, the other have low scores. It's just they have nothing to do with each other. If you know one, there's no prediction of the other. Do you see that? Is that clear? Okay. Now, I don't know 100% certainty. I can't imagine there being knowing what the temperature is here in South Lake Tahoe would tell you anything about some soccer game score in a high school in New Zealand. Okay. let's see if you can come up with an example of a two variables where R is very close to 0. So there's pretty much no real correlation. Okay, I think you say the price of apples and the GPA of college students. So maybe you would say instead that because there isn't like an X comma Y on that. So you'd have to change that a little bit to maybe the price of an apple that a college student buys and that college student's GPA. Does that make sense? There has to be a person that does both. So tax brackets and latitude of address. Okay. That might actually have some correlation. Not sure, but that one might because there's definitely some areas that they make a lot more money. So I'm not sure about the tax bracket and latitude. I would guess there would be a correlation of that. And if you're thinking of America, if you're thinking in the world, it's definitely a big deal because south of the equator makes less money than north of the equator on average. Does that make sense? So I think tax bracket and latitude would have a correlation, a non-zero correlation. Okay. But hopefully you get the idea of what it means to have a correlation close to 0. Basically means that knowing one is not going to help you find the other, especially using some line. All right. So now let's see if you can come up with an example where the correlation is close to -1. And my example is, how about how many cigarettes a person smokes every day and how long they live? I hope you all know that if you smoke a lot, then your probability of living long is lower than if you don't smoke. Do you know that? Hopefully you've heard that before. Okay, doesn't mean you will die tomorrow if you smoke, but it definitely, increases your odds of an earlier death. See if you can come up with an example where R is close to -1. How much time is spent studying and the scores of college students' exam. I would hope that would be close to 1, because if you spend a lot more time studying, hopefully you'll do better on the exam. Does that make sense? So they both, as one goes up, the other goes up. And that would be close to 1, not -1. Number of items available and the price of the items. So if there's a lot of items available, then the price was lower. Remember, as one goes up, the other should go down. But if the price is lower, wouldn't everyone buy it and then it wouldn't be available anymore? Right? If the supermarket decided to charge, $10 a pound for an apple, no one's going to buy it and they're going to have too many apples. Does that make sense? So it depends what you mean by items. If you're talking about food items, I think it's a positive correlation. If you're talking about items that are not necessarily in a market, that would make sense. So that might be, let's say, the number of a special type of coin that has been printed versus the price of that coin. That would work. Do you see that? Because then if there aren't very many coins, then collectors are going to want it and it's going to get more expensive. Is that what you meant? So again, you want to be specific, otherwise it can go either way. Okay, if it's not a good product, then no one's going to sell it. Because no one's going to buy it, so why sell it? Do you see? And you're not going to sell it for much money because nobody wants it. So I don't think it would be for products like that. It's more for special items like coins or something. The amount of time a person spends at a job and the amount of time they spend studying. That could be. That could be. Okay, Dollar Tree used to all be the same. And if it's everything's the same, you don't even do regression analysis. It used to be everything was $1. Now things have changed a little bit, but so Dollar Tree wouldn't quite work. Does that make sense? Because the X's and Y's both have to vary or you don't do regression analysis. Okay, I want to talk about R squared now. And by the way, just to let you know, if R was say 0.2, R squared would be 0.04 because 0.2 squared is 0.04. But it's a lot more than just squaring the number. So and this is often thought of as the hardest part of the whole chapter. So pay attention to this piece. This is tough. Okay. So R squared, first thing is the square of R. That's easy. So it's better to make it a percent instead of a decimal because it's easier to understand. So what we can say is you can think of the variation in the dependent or the y variable is kind of big. But if you only look at y values that all have the same or similar x values, then that variation will be reduced by R squared percent. Okay, and variation is kind of like a standard deviation. I'm not getting into the details of the math. I want you to understand the ideas. Does that make some sense? All right, so R squared was really small, actually. 0.002, I guess, rounded to 3 decimal places. So that's 0.2%. So we can say is the variation in the number of minutes per week people exercise is quite large. Okay. And it was. I mean, I exercise a whole lot, and some of you not so much. But if we just look at the cohorts of people who all have the same number of siblings, then on average, the variation of exercise per minute will go down by, in this case, it was just 0.1%. So that tells you that if you know how much they exercise, if you know how many siblings they have, then it actually doesn't change the variation at all. It doesn't give you much information at all about the amount of exercise someone does. Any questions on that? Okay, so let me give you another example. Let's suppose the city population size in thousands is the X variable. And the crime rate per thousand is the Y variable. Okay. And let's suppose that R was negative 0.36. So by the way, we say we have a weak negative correlation between city size and crime rate. Because remember that to be a strong correlation, you're either close to -1 or close to 1. To be weak, it means you're close to 0. And 0.36 is somewhat close to 0. It's not like the 0.002, which is super close. Okay, or actually it wasn't 0.002, it was 0.04, which is really close to 0. So negative 0.36 is still weak. Okay, R squared is the square of 0.36, which happens to be rounded to 2 decimal place 0.13 or 13%. Any questions so far? So what we can say is there's a large variation in crime rate to city. Okay. So if we look at, New York crime versus, let's say, Sacramento's crime rate versus Myers' crime rate, that crime rate's gonna, it's gonna change a lot. Do you agree? Okay. But if we only look at cities that have a similar population sizes, then the variation in crime rate is going to be reduced on average by 13%. So we can think of like 13% of kind of the knowledge of crime can come from knowing how big the city is. And the other 87% will come from other things. What other things might be important for crime rate? Okay, no, this is by city though. This is a city's crime rate, not the city's. Yeah, income. I think income be so if you looked at the average income of a city versus crime rate, my guess is you're going to have an R squared that might be 0.8 or something or 0.6. Do you see? And then knowing knowing how, wealthy a city is will really help you in understanding what the crime rate is. Do you see? Because that R squared is going to be much higher. Any questions on the idea? All right, so what I want to do, and I'm going to spend some time on this, I want to go over, in my opinion, the most important statistics that's ever happened in my town of South Lake Tahoe. Anyone know what that is? And it was regression analysis, it turned out. COVID was important in the world, but this is our town in Tahoe. This is important in Tahoe, not important anywhere else, really. But we cared about it a lot, and others hardly even knew. Yeah, water quality. Water quality. Okay. So I don't know if you know much if you're in Tahoe. I know some of you are in Tahoe, right? But hopefully you know that they measure the depth of clarity every year. Okay. I don't know if you know about that, but they measure how deep if you drop what's called a seki dish, which is kind of like a plate, a white plate. You drop it down in the water until you can't see it anymore. How deep until you can't see it anymore? And that's called the depth of clarity. And you may or may not know, but the ones who are in charge of doing the science of that are UC Davis. So UC Davis scientists, professors, and they do it every year, and they've been doing it for a while. So not too long after I got here. Okay, do you have to have perfect vision to do it? Yeah, you better have pretty good vision. So the person doing it is going to have good vision. The person that has bad vision, that's not the person that's going to be, doing the test. Yeah, if you're blind, forget it. You can't do anything. You're never going to be able to see how far. Okay, so you gotta have pretty good vision. And vision means like I'm wearing glasses, that's fine. Okay, because my vision's great with glasses on. All right, so not long after I got into Tahoe, just about 4 years or so, the most important person in all of America came to Tahoe. Anyone know who that was? Yeah, the President of the United States. Anyone know who it was? 24 years ago? That's okay if you don't. It's history, it's not math. President Clinton? Okay, so he actually came to Tahoe. And the cool thing is, I heard about this from my student who was there serving him at a restaurant. And one of the good things, and I'll tell you, I wish all presidents understood statistics. but President Clinton actually understood statistics, is they were able to show President Clinton regression analysis on the depth of clarity in Lake Tahoe. And this is the picture they gave. Okay. And those of you who are in Tahoe, you might have seen this picture before or some picture like it. Have you seen it? Haven't seen it? Okay. But this is a major picture in Tahoe. Now that I told you next year you'll see it. It's in the newspaper every year when they do the measurement and when they do the, decision. And what they did is they drew a scatter plot. All right, you ready for a trick question? Do you think the correlation is positive or negative for this scatter plot? What do you think? Yeah, it's a trick question. Wow. Usually when I say it, my students always get it wrong because they don't see that if you look at the x-axis, you have 35, 30, 25, 20, 15. It's upside down. So it's actually this particular one's upside down. It's they do it so they can kind of picture the depth of the dish under the boat. But it's actually a positive correlation. Okay. Yeah, I always say trick question, and most people still don't hear it. They don't think. But you're great thinkers. That's what that means. All right. And what I was able to do, the good thing about the UC Davis people, they're great about sharing whatever. So I asked them and they gave me the data values instead of just a picture. And here's the data values. So do you know what these values are? 68, 69, 70, 71, 72, 73, etc. Do you know what those are? You know what they represent? No, they're not feet down. Definitely not feet down. Yeah, they're year. They're year since the year 1900. Okay. Remember, this is President Clinton. This was, he came in like the year 2000, so they knew in the late 1900s. So this is the year. And then this 32, 28, 30, 28, etc. That was the depth of clarity. Any questions on that? Okay, so the next thing let's do, again, we see a scatter plot, but one thing it's kind of upside down. Let's see it better. So I'm going to copy and paste. I made it easy with commas in it. I'm going to new plot. I'm going to paste. I'm going to grab the y variable, copy it, and I'm going to paste. And let's plot points. What do you notice? Okay, because now we have one that's not like some boat thing. Now it's actually a math scatter plot, and it shows a line. Does it look like a pretty good correlation? Does it look like a correlation that's useless? That's where it doesn't help to have regression analysis at all? What do you think? Is it clear there's been a trend, or is it not clear there's a trend? Yeah, there's definitely a trend. Now remember, the word trend does not mean that every year lake clarity's gone down. So for example, in 1981, we were way down here. And then 1984, we were way up here. Clarity went way up. Do you see that? So just note the exams don't have a huge number of variables. They do have variables, though. You get to type. Okay, is it climate change? I'll talk about that in a bit. And that'll be towards the very end of this little discussion on this particular one. And I'm gonna hold off and we'll see. But what we can do is the following. R is now negative 0.847. So that tells us that we have a pretty strong correlation about negative 0.85. Do you see? Very different. Climate change is a little bit based on regression analysis. Mostly it's based on actually chemistry. I can't, by the way, I was a chemistry minor and I took a whole course on it, on that kind of stuff. But I don't have time to explain it all to you. But I can talk to you in office hours if you want to come. But it's a little hard. So I'm not going to get into the climate change right away. R squared is 0.71 or 72 if you round to 2 decimal places. So that tells you that there's been a big variation, right? We can see, like over here, we only had a depth of, like in 1990, maybe 95, we had a depth of clarity of around 20 meters. But in this year, 1967, the depth of clarity was like 32 meters. Huge variation. Do you see that? There's been a big variation in depth of clarity. Okay, but if instead of looking at the whole picture, if we just look at clusters of years, like in this little cluster or this little cluster between 74 and 77, there's still some variation. But on average, that variation is around 72% less than the variation without focusing on any particular group of years. Do you see that? Okay, remember, this is not about cause and effect, but we can say that, yeah, 72% is going to be based on, looking at clusters of years, so the year definitely makes a big difference. But then there is the other 28%, and that's going to be based on other stuff. What other stuff might matter besides the year? How long in years we waited. Okay, sediment. Okay, so let me tell you, if you're not from Tahoe, you probably wouldn't even guess. If you're from Tahoe, you probably would guess. You guess? Should tell you precipitation amount. If there's a lot more precipitation, then you have a lot more flow of water and it's going to push a lot of more stuff into the lake. And that happens to be another big predictor. But it's really hard to change the amount of precipitation we have. That we can't do. You can't change the year, but we'll talk about what we can change. Any questions so far? Okay, so there's R and R squared. Yeah, so as more years passed, the Lake Tahoe quality tended, I'm going to do past tense, to go down on average. Why am I using past tense? What's the most recent year we have in this picture? Already happened, but even the most recent year was the year 1999. Yeah, this is what President Clinton was looking at. Okay? Then we have the equation. We have a line. And again, you might not have seen this stuff since like 9th grade or something. Maybe more recently. But lines have equations. And you remember what the equation of a line looks like? Y equals? Yeah, you've seen mx plus b. In statistics, I know you're going to hate this, but we usually use a plus bx. There's reasons that I can't explain. High math stuff. But the point is going to be a number times x, and there's going to be a number that doesn't have the x. So the number next to the x in this case is negative 0.2465. That is the slope of this line. And the number that's not in front of the x is about 45.6. And that's the y-intercept. Any questions on that so far? Okay, so now that we have that, we can start interpreting it. So hopefully you remember, when you look at the slope, Do you remember these words, rise over run? I know it might have been a while for you, but those words happened. Yeah, so rise over run. The slope is a fraction. The rise is how much the y variable changed. The run is how much the x variable changed. Okay? And if you have it in a decimal, like 0.25, for example, rounded to 2 decimal places, you can always make it a fraction by putting it over 1. Kind of lazy, but it works. So you can say negative 0.25 over 1. So now the rise is how much y changes. And y, in our example, was our depth of clarity, our meters. The run is how much x changes. And in this case, x was the date or the year. So the bottom, we always let be 1. So that means the year changes by 1. So here's how we can interpret it. For every year that passes, on average, okay, the lake clarity has tended to go down by 0.25 meters. Okay, I want to mention tended. You can't say will go down. Never ever use that word will. Okay, it's only a tendency. Okay, also it's an average, so I put on average. And 1 means 1 year, and that's why every year. Every 1 year. Do you see? Any questions on this? By the way, especially those who are in Tahoe, do you think that's okay? If on average, there tends to be a drop in clarity of 1/4 meter every year? Yeah, no, that is a horrible disaster for our lake. Okay. Okay. You can only mathematically test an economic tendency if you have a correlation that actually is meaningful, so not close to 0. Do you see that? If it's close to 0, then it's useless. Do you see? Does that make sense? But if you do have a strong correlation, definitely use it. And definitely people in Wall Street use it. And I have also, by the way. Okay, let's look at the y-intercept. Okay, the first thing, the y-intercept, hopefully you remember, mathematically, that's the value of y when x is 0. Do you remember that? So that's what y-intercept means. It means plug in 0 for x, get y. Okay, on the other hand, 0 for x is the year 1900. If you look at our data values, do we have any data value anywhere in the vicinity of the year 1900? No. They didn't start measuring lake clarity until 1967. So you could not even talk about it really, or you shouldn't. If y equals 0 is not anywhere in the vicinity of any of the data values, then the y-intercept isn't very useful. Similarly, if the x value, let's say the x value was -10 instead of what we got. That would also be stupid because you can't have a -10 meters of lake clarity. Right? The least amount of lake clarity you could have would be 0. Do you see? Okay, so in this case, the y-intercept wouldn't really have any relevance. Is that clear? Any questions on that? Okay, if it had relevance, then it would be the best prediction for y when x is 0. So you could say our best prediction for lake clarity in the year 1900 is 45.6 meters, but it's not a good prediction at all. Any questions on that idea? Oh, think I copied this from a few months ago. Let me change it because I'm asking a new question. Okay, so what is the best prediction for lake clarity in the year 2024? So again, imagine, Clinton, it was, the president of the United States and also some senators were in a room, being shown this by UC Davis. And then they said, well, let's see what it would be in the year 2024. Okay. By the way, the year 2024 has Y value 124. It's 124 years after the year 1900. That's where we are now. How do we find the best prediction for today? Any guess? The hint is it's pretty easy. Test the results. Well, remember that we're imagining being in the room in the year 2000. So at that point, they couldn't test the results. 24 years ahead of time. Yeah, we plug in 124 as the x in this equation. So we have this equation. I'm just going to copy and paste it. But now x is going to be times 1, 2, 4. And now, I think the easiest is now I'm going to copy that. I'm going to go to the scientific calculator, put that in, and you get 15 point, basically 15. So that is 15. Any questions on that? By the way, do you think that's okay? Do you think that would be okay? To have a lake clarity of like 15 meters when it was, like over 30 meters when they first measured it? That's not okay. Any guess on what happened? What, fortunately, but President Clinton and the Congress people did? Yeah, legislation. And they funded millions of dollars actually to battle the clarity issue, the loss of lake clarity. And they did that, 24 years ago. It passed like within a year. And by the way, do you think it helped? All right, what I have now. This is a more recent picture. Look at the year 2000 to the year 2020. What do you notice just about that part? What's happened with the clarity of the lake? Yeah, I wouldn't say it stayed even, but we didn't have a tendency of a downward tendency over the years. Is that clear? There are still ups and downs, and that's going to happen because of, like I said, weather. Lots of rain, lots of snow. That's going to bring some, a lot of dirt in the water. But over the long run, really, there wasn't a continuing decline. Remember I told you this is elementary stats and I can't get into more advanced stats? And the lines can't curve, but what you can do is you can have different kind of predictors using advanced stats, and I can't go there, sorry. So if you really want to learn it, you need to take an advanced stats class with advanced math, by the way. Good luck. So you might have a lot of work to do. Okay. Yeah, so that's just a big note. And the UC Davis professors do have that background. Okay. So do I, by the way. Okay, but we're not going to do that. We're going to just realize that, hey, if you look at just the last 20 years or so, correlation has gone to almost zero. Do you see that? Any questions on that? So the big, it worked. It mattered. Okay. Okay. So money does fix problems. It can, not always. But in this case, it made a big difference. Money did fix problems. It doesn't always fix problems, by the way. But this time it did. Okay. So just some big notes. Do never, ever, ever use the word cause when you're talking about correlation if all you have is data and like R and R squared. Okay. And you may or may not know, you may never have thought about it, but if you look at the word because, what do you notice if you get rid of the first two letters of because? Cause. Do not use the word because. Got it? It's another one to avoid. It's really the same. Another one, which doesn't look like the word cause, but it turns out it's the same, is don't do the old if, if this one changes, then the other one will change. That also is cause. Do you see? Any questions on that idea? All right. By the way, if you do want to show about causation, so now I'm going to get into the climate change idea. If you do want to show that carbon dioxide increasing in that is causing global temperature to increase, it's a two-step process. Step one is regression analysis. Okay, but it has to be two-step. If that's the only step you do, then you can't say that the carbon dioxide has caused global climate change. What's step two so that you can get causation? Anyone know? It's really important for things like climate change. Yeah, experimentation in this case probably isn't going to work because we're not going to be able to experiment by let's try it. We're not going to all of a sudden throw so much carbon dioxide that it could destroy the Earth. So step two is science. So step one is do correlation to say, hey, we have this correlation. And then you go to the scientists and you say, can you see if there's any science, like chemistry, behind carbon dioxide causing climate change? Does that make sense? So it's a two-step process for causation. Without the science, you cannot use the word cause from only having regression analysis. Does that make sense? Okay, the only other time that sometimes you can do it is when you have like randomized control studies. Because then the only thing that could be would be cause. Okay. Any questions on that? So another example that I like to give for cause, do you think there's a correlation between the amount of gray hair a person has and their age? Do you think there's a positive correlation? Yeah, yeah. Okay. If you look at 20-year-olds, you're not going to see a lot of gray hair. If you look at 60-year-olds, you're going to see a lot more gray hair. Do you see that? Does that mean that if I went and dyed my hair gray, it's going to make me a lot older? No, that is not going to cause me to become old. Do you see that? It might cause me to look old, but it won't cause me to be old. Do you see? So that's an example where there's definitely not causation. Okay. It turns out the causation's in reverse. Age causes gray hair. And that you can do with biology. Okay, which I can't get into the biology and chromosomes and all that kind of stuff. But there's stuff that happens when you get older that makes your hair go gray. but the gray hair doesn't make you older. Do you see that? Any questions on that? All right, let's talk about hypothesis testing. So a major thing that you need to do in regression analysis is you need to see if there's a correlation or not. Okay? If there is no correlation, then don't even think about using the regression line to make a prediction. Okay? If there is a correlation, then that regression line is probably useful. Do you see that? So here's the good news for y'all, but listen carefully because you're going to be tested on it. The H naught and H1 are always exactly the same. So you must, on the exam, when I say write down the null and alternative hypothesis, if it's coming from a chapter 12 question about correlation, H naught, colon, rho equals 0. Okay? Again, if you don't know how to type the letter rho, you can always write RHO. That's how you spell it, it turns out, in English. In Greek, of course, you spell it that way with that letter. Equals, in our class, we're always going to be 0. And H1 in our class, rho not equal to 0. And again, if you don't know how to type the not equal sign, you can write NOT and then equal sign. Is that clear? Because there are times, this is elementary stats, we can't do everything. But there are times you want to not just say the correlation is not equal to 0. Sometimes you want to say there is a positive correlation. But I'm not going to test you on that. Sound fair? Okay. So the good news is, here it is. And even on the calculator, you have 3 choices. But if you don't click anything, it'll always do the not equal to. That's the most common. All right. It turns out, I can't get into the math of it for you guys, but the test statistic is still the student's t-test. And that's negative 8.73 about. Is the p-value about 9.67? No. How come? Yeah, you got to move your eyeballs to the right and see that E negative 10. Okay, P's can never be over 1. If you ever say the p-value is 9.67, you screwed up. By the way, R and R squared can't be farther away from 1 either. Same thing. They're always between -1 and 1. R is always between 0 and 1. P-value is always between 0 and 1 also. So the p-value here is going to have 9 zeros before this 967. So our p-value, let's write this down. Will be equal to 0.1, 2, 3, 4, 5, 6, 7, 8, 9, and then 967. Okay, any questions on that? Very, very close to 0. Yeah, sorry if people are getting confusing. They are different letters. One Greek, one is English. Sorry about that. But they are, the way I type them, that's the Greek letter, the little curvy. Why did I 9 zeros? Because it's E negative 10. That means we move the decimal over 10 places. The first place, nothing happens. All the rest of them, you'd have to gather a 0. Does that make sense? The E negative 10 moves the decimal place 10 places. Does that help? If there is an E negative 10 at the end or E negative something at the end, then you're always going to move that decimal place. If it doesn't show an E negative something, then it means the decimals don't move. I want to give you a heads up though on a smartphone. So if you're using an iPhone or something, your screen may only show this amount, and if you don't scroll, you won't see the E-10. On a computer, you're fine, but on a phone, sometimes it doesn't show the whole thing, and you gotta like move it. Does that make sense? And that's just a technology thing. Okay, so we could say there is very strong, statistically significant evidence to support the claim that there is a correlation between year and lake clarity. Any questions on that? Okay. Now, if you have a very strong statistically significant evidence of a correlation between year and lake clarity, does that mean that having later years is going to cause the clarity to get worse? Yeah, no, don't ever use that word cause. Got it? I want to mention one thing about sample size. And in our example that we originally did, maybe I'll scroll way up. What was our sample size? Yeah, it's 5, very small. It means, hopefully you know from this class, it's kind of useless. Do you agree? Okay. So that's just a note. Whenever you have a sample size that's that small, you should pretty much say, no, we need to get more data. We need to survey more people. Does that make sense? Okay. On the other hand, this sample size was much bigger. Okay. It was what, 92, I guess? I mean, 32. So this was a big enough sample size, but even if they had a smaller sample size, it turns out that UC Davis did something that, and I taught, by the way, I talked to the researchers. I was actually had a conversation with them about this, about their statistics. And I asked them about how they collected their data so that they have reliable data. And what they said made me smile so much. Something I like never heard anyone else say that was doing science. And that is one of the things you have to think about is how many days are there in the year? Let's say this year. This year is different than next year. Yeah, there's 366 days in this year, right? Right, because this year was a leap year. Okay. And what they did is they didn't have the time to survey every day. So any guess how many days they surveyed? The hint is it made me smile. No, not one. That would make me frown. Then I'd say, what a stupid idea. You have terrible data. All right, you're not guessing. Should I tell you? 31. Why do you think they use 31 days each year? Yeah, because they took the average of those 31 measurements that they did. They took the average of the 31 measurements. And then from that average of the 31 measurements, they plotted that point for the number of meters. So each of these values actually follows a normal distribution. Isn't that kind of cool? Approximately normal, because they took averages of 31. Is that cool? Do you see why I smiled? I almost never hear someone say that, but they were doing the science just right. Okay. There were some other things they talked about, which was cool too, that wasn't math. Like they did it on sunny days because if there's clouds, then the clouds can affect clarity in terms of how far you can see. No, in our class we do 31, remember? You say 35, but in our class 31 is enough. Because over 30 is our class's special number. So 31 is the smallest. Any questions on this? Is that cool? Kind of cool? Okay, so just a note, I want to mention a few things about, maybe I'll give you this first before. So first thing, if one more example, because we do have some time. Let's say you looked at the years of successful education after 10th grade and the salary at 30 years old. Do you think there'd be a correlation between those two numbers? What do you think? Yeah, yeah. So it turns out there is a strong correlation. R is 0.91. Okay. If you don't even graduate from high school, there's a good chance you're not going to make much money. Does that make sense? If you graduate from college, you're much more likely to make a lot more money. Does that make sense? If you have a master's degree, you're probably going to make a lot more money. Any questions on that idea? Okay. Now we can guess at that, but even better than guessing is to collect data. So let's suppose we collected data, and let's suppose R was 0.91. Then we could say 0.91 is a strong correlation. Do you agree? It's pretty close to 1. So there's a strong linear correlation between the number of years of successful education after 10th grade and the salary at 30 years old. Okay. By the way, if it was salary at, say, 20 years old, it probably wouldn't be that great a correlation. It'd probably be a negative correlation, actually, because 20-year-olds that are in college and not making much money. But 30 years old that's enough to see it. Any questions on this idea? Okay, if you square 0.91, you get 0.82, it turns out. So I'm just going to give you basically another important example. So we could say there's a large variation in salaries at 30 years old for 30-year-olds. Do you agree? Some people make a lot of money, some people don't make much money. Is that clear? Okay, but if we look at 30-year-olds who all had close to the same number of years of successful education after 10th grade, then that variation on average tends to be decreased by 92%. It's not the salary that's decreased, it's the variation. So if you look at all people, let's say that had, say, 2 years of college, then their salaries are going to be much closer to each other than if you just look at people in general without asking them about college. And how much closer? On average, 82% if you looked at all the different years of college. Do you see? Each individually. Okay. I don't think I wrote it down here, but let's write this down. Y was equal to negative 27.3, I'll go 1 decimal, plus 16.4 x. Okay, so when I put it in the calculator, that's what I got. I want to save some time. Hopefully you understand sticking the calculator is not that hard. Okay. So let's use a line for x equals 6. So let's say 6 years. By the way, 6 years of education after 10th grade, what is that typically about the person? What does that tell you about the person? Yeah, they probably have a bachelor's degree, almost certainly not a master's. Does that make sense? So we would take negative 27.3391 plus 6.4084 times 6. And what I got was 71. So our best prediction for someone with 6 years of successful education after 10th grade is that they'll earn a salary of $71,000. Okay, notice it's a best prediction. It doesn't mean that it's a cause. We don't know for sure. It's just a prediction. Any questions on that? Okay, the slope is 16.4. Again, that's the rise over the run. So 16.4 is how much Y changes, which is how much the salary changes. And this is in thousands of dollars. The run is, we can call it 1 because we're putting it over 1. That's 1 year of education. So for every additional year of education after 10th grade, on average, the salary tends to go up by $16,400. Any questions on how I made that interpretation? Any questions? Okay, let's look at the y-intercept. So first thing, is it possible for somebody to not have any education after 10th grade? Yeah, that can happen. Is it possible to have a salary of negative $27.3 thousand a year? No. Okay, so there's no relevance. Okay. If there was relevance, we would say that, hey, if a person doesn't have education, that means they're making negative money, but that's, well, you can owe money, but if it's your salary, that's the amount you get paid to work. Nobody gets paid negative dollars to work. Then you don't call it work. Does that make sense? Then you call it play. Because you have to pay to play, but you don't pay to work. Does that make sense? And inflation, yeah, is still positive. Your inflation goes up, actually, not down. Your salary goes up with inflation. Any questions on that? Any questions? So are you understanding this whole idea of regression analysis? Okay, the secret word, by the way, I'm going to say a little more after this, is because. The salary, the value of the salary would go down due to inflation. But remember, the y-intercept means at 0, your salary is negative 24,000 or whatever it was. Negative 27,000. Does that make sense? It's not how much it goes down. This is the salary for a person, a predicted salary for a person who has no education after 10th grade. And you would never predict a salary of a person to be negative 27,000. Does that make sense? So the secret word is because. Okay, and as I mentioned, beware of that word, the word cause in because, but that is a secret word. I always like to put in an important word for the day. That is a secret word for what we're doing. And I want to mention a few things about regression analysis. Now that we've had our secret word, this is more general stuff. And that is, I just spent an hour and 25 minutes talking about regression analysis. Okay. Do you think that's enough time to fully understand everything about regression analysis? No. So I do want to let you know that just because we don't talk about it does not mean it's not used in the world. Any questions on that idea? So let me tell you about some things that regression analysis is really important in. Okay. So one thing is that if you look at what we just did, like y equals negative 45, 45.6 minus 2.2465x. There's an x variable x, and there's a y variable y. I do want to let you know that if you get into the very advanced regression analysis, which won't be this course, but I want to let you know in case you're, looking at an article or something, often you have more than one variable. Okay, and you can still do regression analysis, just not in our class. So for example, in your discussion posts that you have to do not do anything where they use more than one variable, because that's not what we're talking about. Make sure that you have something that truly shows regression analysis for a y versus an x instead of a y versus many x's. Okay? So it's complicated in terms of how many dimensions. Let me tell you, at least for this year and last year, any guess on how many variables was the most important regression analysis that was done? Any guess? Okay, it turns out thousands of variables. What's the big thing that's happened in the last year? In terms of using some kind of big statistics to do something. COVID was not the last year. COVID's the last 4 years, maybe 3 years in terms of the vaccine. It's another big biggie. Everyone's talking about it. Election, that's the next year. Not so much a year ago. AI. I'm sure you've heard of artificial intelligence, right? Have you heard it? Okay, ChatGPT, for example. I cannot get into the details, but you're sick of it. Okay, don't just say it's going to go away, because it won't. And I want to let you know it's all about regression analysis. Okay, but it's thousands of variables. It's very deep, but that's a big, big, deep regression analysis. And I cannot get into, it's a tool, not a person, that's for sure. But it's an important tool, and it's going to be used a lot. It's already being used a lot. And that's thousands of variables, but it's regression analysis with many, many, many variables. Okay, that makes sense? Do you believe that there's a lot of variables involved when a computer makes a decision with AI? And there is. Okay, so a lot of times there's a lot of variables. So just I want to give you that, note. They call that often multiple regression analysis, or multivariable regression analysis, you'll hear too. So regression analysis is a lot deeper than what I told you. Okay, actually, that's not why it makes so many mistakes. Having a lot of variables is actually a good thing, not a bad thing. I can't get into the details. It's very intense math. So, but trust me, it's a lot of math. Okay, so that's a biggie. I think I should mention it because it is going to change the world in the next 10 years. Mark my word. If it doesn't, you can laugh at me. But my guess is you all know it's going to. Okay, kind of like the internet did from when it started to 10 years later. Okay, so regression analysis is a huge part, and it's used in lots and lots and lots and lots of things. Okay, any questions? 7:30, which is around when we like to be done. But I think I'm going to stop the recording.